In this video we are looking at how vsepr theory can be used to predict the structure of molecules. So we've got one example of beryllium dichlorides where there are two bonding pairs of electrons. So we want to get those bonding pairs as far away from each other as possible. And the easiest way to get them away from each other is to have them in this linear arrangement. Okay, and in this linear arrangement that minimizes the repulsion between the electrons in the beryllium-chlorine bond. So when they're rotating around the beryllium, they're constantly as far away from each other as possible. And this gives them a bond angle of 180 degrees, which has been calculated because a full circle would be 360, and then divided by 2 to make 180. And an example of beryllium trichloride. Again, there's not my full octet of electrons, so I have 6 electrons this time. So to minimize the repulsion, I order them in a trigonal planar geometry, where I can see that it's trigonal because it looks like a triangle, and each of my bond angles in this case is 120 degrees. So I'm getting a smaller bond angle. That's not a surprise because there's more atoms present. In methane, if it was a two-dimensional molecule, I would have a bond angle of 90 degrees, okay, because I had 4 electron pairs. However, I could arrange this in 3 dimensions in a tetrahedral arrangement. So you can see there at any one time, one of my hydrogens is pointing out of the plane. One of my hydrogens is pointing behind the plane, and 2 of my hydrogens, the top one and the right one, are in the plane of the molecule. Okay, so I get a bond angle of 109.5, which is obviously a bigger angle than 90 degrees, so that minimizes the repulsion better. If I had an octahedral complex, we would see that I could have an octahedral geometry, which is basically 2 pyramids built on top of a square plane. So I could have 6 electron pairs in total, and with those 6 electron pairs I'm getting an expansion of the octet, so I have 12 electrons in total. 4 of those pairs would be in the plane of the molecule, so within that square that you can see drawn out now. 1 would be above, 1 would be below, and I'd get a bond angle of 90 degrees. If I have 5 electron pairs, I've got a trigonal pyramidal geometry, and I've got 2 different bond angles, one at 90 degrees and one at 120 degrees. Okay, again, in my octahedral geometry, my bond angle is only 90 degrees. Okay, so the trigonal pyramidal, I've got 2 different bonds, 90 and 120, and in my octahedral geometry, I only have the 90 degree bond angle. Okay, so all the bond angles in my octahedral geometry are the same, whereas in my trigonal pyramidal geometry, the bond angles are 2 different bond angles. So the one above and into the plane, and then the ones within the plane. The ones within the plane you can see are a trigonal planar geometry, so that's my 120 degrees. Okay, I can look where I'm starting to get lone pairs in the molecule. So an example is ammonia, where I've got 1 lone pair on the nitrogen. Okay, so I've got 3 bonding pairs, which are being flashed up now, and 1 lone pair. Okay, so I would ideally like to have a tetrahedral geometry, because I've got 4 electron pairs. Okay, so my geometry is based on a tetrahedron. However, the fact that I have that lone pair in the ammonia molecule means that the tetrahedron gets distorted slightly. So, therefore, my bond angle is decreased from the ideal of 109 to 107 degrees, because I've got an increased level of repulsion. A second example of water. Again, I've got 2 bonding pairs. However, this time I've got 2 lone pairs. So again, my ideal shape would be a tetrahedron with an ideal bond angle of 109.5 degrees. Again, this time, because I've got 2 lone pairs, my tetrahedron is even more distorted. So I need to organize my lone pairs so they are as far away from each other as possible, so that's why they're pointing in different directions there. And I need to organize my bonded electrons as far away from each other as possible. So I end up with this V-shaped molecule, or you could also call it bent. It has an angle of 104 degrees, which is lower than the angle of 107 degrees because of the extra lone pair. Okay, so I've got extra repulsion because I've now got two lone pairs rather than just one. Okay. The second important thing to note is within the molecule which is actually having the most repulsion. So we can look at an example of SO2 here, and we've got within the SO2 molecule, I've got one lone pair on my sulfur. I've got a sulfur which has been singly bonded to an oxygen, and a sulfur which has been doubly bonded to the right-hand oxygen. Even though there's 4 electrons in that double bond, it is treated as one bonding environment. So I have a total of 2 different bonding environments, the double bond and the single bond. So my ideal bond angle would be 180 degrees with my 2 bonding environments. However, the sulfur lone pair reduces that bond angle because of the repulsion. So I'm getting a V-shaped molecule again. However, this time the bond angle is not going to be as low as 104.5 degrees. There is still going to be some repulsion that's shown there between the electron cloud and the bonding pair. I would have 3 electron pairs in total, so I'd expect a bond angle of 120, but the lone pair reduces that bond angle. Okay, so we've seen different examples where we've got different amounts of repulsion. So we can summarize this with a table, or we can say that a bonding pair bonding repulsion exists, but it's the smallest amount of repulsion. Bonding pair lone pair repulsion is the next biggest, and lone pair repulsion is the biggest still. So that's why water has a smaller bond angle than something like ammonia, for example. Okay, we can look at some extreme examples, so rarer examples. So this one is SF4. So we would ideally have 5 electron pairs. So we've got 4 bonding pairs and 1 lone pair. So we would be ideally looking at a trigonal pyramidal structure. Okay, and with a bond angle of 90 degrees and 1 bond angle of 120. Okay, however, because we've got the lone pair arrangement, we're reducing that bond angle. Okay, ClF3 is another example. So this molecule is T-shaped. So we'd expect it to be trigonal pyramidal with the 5 electron pairs. However, the 2 lone pairs take up 2 of the positions, which give it its T shape. Okay, with a bond angle of 90 degrees because the chlorine molecules are in the same plane, and there's a second bond angle of 180 degrees between the linear fluorine atoms that are joined to my chlorine. Okay, and I can take the rare example of I3, which is an ion, which is going to have a total of 3 lone pairs and 2 bonding pairs. So again, ideally it would have a trigonal pyramidal structure. Okay, but because 3 of those locations are taken up by lone pairs, it reduces the bond angle. Okay, so now the bond angle is going to be around 180 degrees because we're all in a linear arrangement. Okay. And then finally we can look at unusual molecules that are going to take an octahedral complex. So if we look at BRF5, for example, we would have an ideal shape would be octahedral for the 6 electron pairs. But because one of the electron pairs is a lone pair, it reduces the bond angle, and we have what we call a seesaw arrangement. So the bond angle is still around 90 degrees, but slightly reduced. Okay, if we had two lone pairs in an octahedral arrangement, so for example xenon tetrafluoride, right, the shape would be what we call square planar. So the lone pairs would move far away from each other as possible, taking the top and the bottom positions, and then the four fluorine atoms would be left in the square plane, so again we'd expect a bond angle of around 90 degrees with that. Okay? We can then look at molecules and organic molecules and what the bond angle within those organic molecules is going to look like. So we can take the example of ethene, which has 2 carbons and 4 hydrogens. Okay, so within that, the 2 carbons would double bond with each other. Each of the hydrogens are only capable of making single bonds. Okay, so around each carbon I've got an octet of 8 electrons. Around each carbon I have 3 bonding environments, 1 for the double bond and 2 bonding environments for the separate carbon-hydrogen single bonds. Okay, so around that carbon-hydrogen-carbon bond I would expect it to exist in a trigonal planar shape because I've got 3 electron pairs for my vsepr arrangement. Okay, so I would expect to have a bond angle of 120. However, because I've got 4 electrons in that double bond, that double bond slightly repels the carbon-hydrogen bond, so I end up with one bond angle slightly greater than 120 and one bond angle slightly less than 120. Okay? And then we can apply this to a molecule like methylamine, okay, where the carbon single bonds with the nitrogen. Okay, so I'm ending up with an octet around the carbon and an octet around the nitrogen, but this time the nitrogen has a lone pair on it. Okay, so around the carbon I have 4 sets of bonding electrons. So my ideal shape would be 4 electron pairs would be tetrahedral. So it takes a tetrahedral arrangement with a bond angle of 109.5 for each of the hydrogen carbon hydrogen bonds. Okay, so we can see the bond angle there of 109.5. Within my nitrogen side, again I've got 4 electron pairs, but this time one of them is a lone pair. So it would take a trigonal pyramidal shape, okay, with a bond angle of 107. Because the lone pair is repelling those bonding pair electrons slightly. Okay? In practice, the vsepr can't actually predict the shape of the molecules. It can simply predict the repulsion that's shown by those arrows. Okay? So, within this molecule, we're actually seeing that it can rotate freely because the carbon-nitrogen bond is a single bond, so in practice the bond angles are never as actually predicted by vsepr because of the rotation around that carbon-nitrogen single bond.